Okay, so I keep working these. It's been a busy week, and I really didn't have the time, as much time as I wanted. But I think I realized I got to step a little bit back and kind of like implement this a bit differently. The folks at HNX responded to my bug report saying that they're gonna fix the thing with the edges, so that's good news. For the moment, we'll keep using the qubit thing. Now, what I will do is I'm just gonna focus on actually just thinking about two edges, right? Because I was trying to think a little bit, sort of take a step back and at least think about two qubits, and I think it's the same for three and for more qubits in general. But the idea of merging, right, like in this example, we start with two initial states, 0 and 0. Then we apply Harmonic gate to both top and to both qubits, right? And then we apply control X, which basically leaves this in D state, which what you would do is you'll go like the routine here that tells us whether we should merge these two edges should ideally, let me just see if I can turn up the light because I think it's a bit darker. Better. You'd basically find whether there's two nodes of the same qubit that are the same. And if so, it means you can merge them. But then it means you can just merge everything automatically, right? So this will become a 0 plus 1. And a 0 plus 1. And so at that point, there's no... Actually, there's really no edge anymore. So... Isn't there no edge anymore? If there are other edges, that's still an edge. Okay, so if there's just one edge left, then that edge doesn't make any sense. But so I just gonna be working on just merge two edges and spit out an edge as a result. The merged edge. Then whoever calls that method, like that function, will just take care of the cleanup of the other edges and nodes and whatnot. Now, to be fair to this, if I'd apply these, let's give it a try. If I apply an X gate and I apply, not an X gate, sorry, a Harmonic gate and a Harmonic gate to QB1 as well, right? And then I apply a CX gate. And what state does this leave me, really? I think I have to probably comment this. I don't have to just run the whole thing again, probably. Because that might leave... This is with the alt implementation of the control node, what I know that I have to manually split these, but I might end up with something different here. Is it still running? Oh god, it's still running. Why is it so slow? There we go. What do we have? Whoa, what the heck? Wait. Oh. I don't want to be doing these, because this definitely... Oh yeah, but that's messy anyway. I do a Hadamard and a Hadamard. Yeah, and then I do a CX. Oh yeah, exactly, because that basically... That's a big split. Like, yeah. So what are the branches that we have? Oh, it's so difficult to read. So I guess the blue and orange are the qubits, and then we have a 0 and a 1 branch. We have a 0 and a 0 branch. We have a 1 and 1 branch. We have a 0 and 1 branch, and we have a 1 and 0 branch, which is basically correct. We have a branch for each of these things. So now we want to merge these, right? So what we have is actually a more generic version of these. We have basically all the possible So we have all the possible, so we have 4 branches, right? And so here we have, why is this so slow? So we have 0, 0, 0, 1, 0, and then we have 0, 1. And I guess we just have, should I make this bigger? And we have another 1, which is a 0, sorry, 1, 1, right? So now the question is, what we should do is we should go and see how, like whether we can merge these branches, right? This is sort of the result of the CX gate because we've applied it locally. Remember, that's a bit of a, I'm playing with 2 different implementations, right? So this implementation is applied 2 qubits gate. It's a bit more generic one. So what it does is it takes these 2 qubits and it actually does a, it applies the 2 qubit operation just locally and then unpacks it into branches. And these particular implementation here is about control. It's just a it's sort of a handcrafted version just for the control gates where I split the control nodes and apply the gate only to the target qubit. The reason I moved to this one is because it would allow me to implement any 2 qubit gates, which I think it's an interesting thing to be able to do, to be honest. And it's just more generic. I think it doesn't matter. So anyway, so you would go through each possible combination of these, and you'd say, okay, so let's pick up these 2 first, right? Can we merge them? Yeah, you realize this is the same. So you merge these into a 0 and 0 plus 1. Yeah, and I guess it doesn't matter in what order you do that. Like you should always end up with an equivalent solution at the end. And I'm ignoring global phases, but I'll have to. The problem that I'm going to have is that this node, like you could have these, right? You could have something like that. Imagine, right? So, and if I compare these to a 0 minus 1, they're the same. So I should be able to deal with this case, but like we'll deal with these later. First, let's just do this simple thing here, where we just we just have these merge edges, right? I'm gonna get rid of this function here. So this just returns an edge. So they give it 2 edges and it returns an edge. So what it does is it goes through all the nodes, right? And if the node in, so if node 1 dot qubit equals, if node 1 dot qubit equals node 2 dot qubit, now we should check whether they're equal, right? Now I should check whether they're equal or there's a global phase. That would be kind of the next case. Should then I just say and I guess I'll need a helper function. Define so maybe state equal, something like this. Well, we're just so we have in the qubit is the state, right? So this is state 1 and this is state 2, and so let's just return for now. So, and those are NumPy, like NumPy complex numbers equality. Can I just do that? I think I can do that, right? I think I can just do return state 1 equals state 2, right? And so here it's an n state equal, right? And I would just say, because that's definitely going to be more complicated, right? To do account for global phase factors. And so node 1 stayed, node 2 stayed. So if this is the case, right, then this is the merge, else. So and we're kind of, in this case, we're kind of done, right? Because we merged that. Returns the new edge. What should it return if they shouldn't be merged? What should we return if maybe not or something? I don't know. I'm just getting a big stop because I'm thinking how is the merging really going to happen? Like, I mean, what if you have like a 0 plus 1 and like a 0 minus 1? You want the interference to happen, right? So should you really just add the complex numbers? I think you should, yeah. And renormalize them? I think you should probably do that. So I think the merging, so now I know I should merge the two edges, right? Because what I think I should do is just have a function that tells me whether I should. So in this case, let's just say return true. And if not, like here at the end, it's just return false, right? Can merge. Mergeable edges, I don't know. And then the actual merge edges, what it should do. And that's the one that returns the edge. It just should return. So the precondition, edge 1 and edge 2 can be merged. Because in theory, that operation you can just do regardless of they're mergeable or not. Like you can always just add these, right? And say, yeah, like the 0 and the 0 plus 1, right? But like even if this would be a 1, like hey, like 0 plus 1, 0 plus 1, but that's not the way, like that's not the way it should work. So you should only be able to merge them if at least one of the elements is equal, right? So this means really you return true only if you find two nodes which are equal between the edges, and that they share qubit, and otherwise return false. And the merging is just basically, so what do you do? So you take, so what you do, right, is you have like a new edge is equal to new entity. Oh, I forgot how to program in a week. How do we do all these? Just like that, H and X entity. Okay. create node, create. Yeah, that's curious how the amplitudes will really have to be handled in here. So far, I'm going to create an entity, and I'll call it just get UID edge, right? And then I'll just do another nested loop, right? And so, which I'll probably be able to avoid once I know. This is just I do that because I need to find for the the qubits, so the nodes are from the same qubit. And then what I would do is I would say, so I need to create a node, right? Can I use create node? Yeah. I need to give it the state vector and the qubit. Okay, cool. So I can just use, I can say create node, right? The qubit is, node 1 qubit, and then the state vector. The state vector is really I don't know if this is going to work out, but like node 1 state plus node 2 state. And now I still need to renormalize. But I want to see at least that it works well, or that it works at all. So I create a node, so this new node, and then I do new edge at element, new node. So I'm adding the new node to the new edge. And then I do these for every node in 1. So I check every node in 2. Right, and I'm under the assumption there's only going to be 1 pair per each, so that shouldn't be a problem with duplicates and whatnot. And so at the end of the day, what we do is return new edge. Cool. So this means now we've got 2 functions, and we can just play with these. See if this works at all. So we're here, and we're gonna now just want to play with these and say, okay, so actually, mergeable. So I give it 2 edges. So let's try the following. Let's say edge 1 equals system edges. I'm gonna make a guess, and I'm gonna do like, because I see we have like 4, 5, 6 edges, but the first 2 will probably be the qubits. I'm gonna do something like that. Can I do these? Edge 1, edge 2, and then I'll say print edge 1. Invalid syntax. Merge edges. None. No, 40. Okay, because the names are oh, I have the get entanglement edges. Okay, so I can do it like these. get entanglement edges system and get the first two. Okay, those are coming in handy actually. Edges, get entanglement edges of the system, and then print edges 0, for example, right? Edge 52. Okay. Elements. Okay, cool. So what if I now go and do, like, for example, print edges 0 elements, print edges 1 elements, right? So we have here, we have 2 edges, and then we have this is called node 85, which is in the 0 state, this is in the 0 state, and this is in the 0 state and the 1 state. So they should be mergeable. So if I say now, so print mergeable edges, and I give it these as parameters, edge 0 and edges 1, and it doesn't print anything. It's not very qubit. Qubit. Yeah, okay, cool, because it's not like that. What I should do, so this is literally edge 1, node 1, edge 2, node 2. That's what we want to do. The same goes for these, and the same goes for these, but with 2. Cool, and I think I'm going to have the same issue here, so this is replaceable with these, this is replaceable with the same, but with 2s. And then, there you go, same here with 2s. Same here, like this. I think that should do the trick. The truth value of an array with more than one of them is ambiguous. Okay. Why? Oh, because it can return true multiple times. Okay, that's not what we want, so mergeable is false, right? False. Okay, merge. So okay, merge equals true. Return can merge. Oh, state equal. Okay, that's the problem. What if I just return true for now? True. Yeah, well, but that defeats the point of testing that. Print state 1. It's an okay. So there's a do arrays. NumPy compare arrays. I guess I should just array equal, because here it's suggesting me to use any or all. NumPy array equal shape and elements false otherwise. Maybe we should try array equal. NumPy array equal State 1, state 2. Okay, that's cool. So it turns true. So they're the same. I like that. Okay, so they're mergeable. So they're mergeable because there's that particular element that does that. And so now, what if we merge them? So what happens if we merge them? Merge edges. Print merge edges, and we give it the same parameters. Boom. No, actually that element. Does it? Of course it does. Add element. Is it like this? Add element. Oh, okay. Okay, so that actually has created. So it does. It's done something. So merged. Ugh. Merged edge equals these, and then I'll just say merged edge elements. Okay, so it's added them. Oh, it's added the thing. It's added the thing. And now I didn't renormalize, right? Because that's definitely a superposition is what we want here, and that's what we want here. It's yeah, kind of. It's done this. How do I renormalize? How do I do that? How do I renormalize the all mass sum app? So on NumPy, normalize array complex numbers. Okay. So two steps would be involved. Offset all numbers by the minimum along real and imaginary axis. Divide each by the max magnitude. To get the magnitude of a complex number, simply use np-abs. Is it what I want to do? Okay, so this is a renormalization with exact values. What I want is I want to renormalize so I want to renormalize so that the the square of the sum of the squares adds up to 1. That's what I want to do, right? What I want to do is that so the sum of the squares, yeah, adds up to 1. What is it doing? It's normalizing everything. Actually, wouldn't these be the no? No, I don't know how I would do that. Normalize quantum state. I don't think that's what I want to do. Oh yeah, okay, to normalize the state vector, we first need the magnitude. Well, indeed, so that is indeed, you divide each element by the magnitude, right? It's just, that's just the way that you define that normalization in general. You just divide the stuff by the magnitude. To normalize the state vector, we first need the magnitude. We get this from a dot product with its Hermitian conjugate. So what is it? To normalize the state vector, we first need the magnitude. We get the magnitude from a dot product with its Hermitian conjugate. For our examples, so this is state vector 2 and minus 2, right? And the magnitude is the square root of the magnitude is the square root of 8. So this gives you that 1 divided by these. Yeah, okay, so you divided the state vector by these, and the magnitude so isn't the magnitude, it's just the sum of okay, so it's just the square root of the sum of squares. So but in NumPy you can, I guess, magnitude, so NumPy of complex vector. That's the magnitude of a complex number. What the heck is this? No, no, no. Audio commercials are not the way to go. Oh no, that's the same thing. Sorry. No, no, no. Back. Oh god. Normalization and array in NumPy. I was here already. Normalize a matrix, normalize a complex value, normalize complex value data. So complex numbers were each coin independently. So real data, imaginary data, and then yeah, no, but that's not is it what we want to do? That's not what I'm looking for. How to normalize state vector. Oh, let's see how Circ does it. Yeah, that should be trivial, I know. To valid state vector. So what does it do? Reshape? Oh no, it does. It just checks qubits in space and stuff like that. Um, mm, normalize a state vector. Take the square root of each number to get the probability amplitude, normalize the state vector, set the vector equal to So that's what we had before. Did these open anything? What is these? Because the total probability system is in one of the allowed states is 1, the square of the state vector has to add up to 1. The square of the state vector, you multiply every element by itself, and then add all the square terms. It's just like matrix multiplication of it. At this point, squaring each term in the state vector and adding them all usually doesn't give you 1, so you have to normalize the state vector by dividing each term by the square root of the sum of the squares. Okay, so that's what I have to do. So the square root dividing each term by the square root of the sum of the squares. So I need to do, so am I, so here I'm adding, so calculating the new state. So new state is, so I take this stuff, and what I do is now I divide these so the is there a smart way to do this in Python? Not in Python, NumPy get vector magnitude. I think that should be something that is a recognition base NumPy's property in array, blah 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 blah. Oh, it's linear algebra norm, so that is the so what is these doing though? This is exactly what it's this is only one way to do it. How do you get magnitude of a vector when you write NumPy in NumPy? I cannot believe that I must specify as a trivial and core. So that gives you linear algebra dot norm. So do I just have to do something like NP linear algebra norm. So the norm is the norm of the new state. And then I say new state equals new state divided by norm. I'm not so sure I know what I'm doing. Oh yeah, there you go. That works. That works. Simple stuff. Okay, cool. Yeah, so I get that. Now, I can't believe this is working, to be honest. Okay, so I've renormalized. It's no longer to do. What I have to do now. Okay, so I guess so I guess now once I have the merged edge, right, I should just delete the edges, the other two, and just add this one, right? Can I HNX documentation? Does this work? Because what I should be doing really is have a function, or maybe I'll just not doing it as a function, but I'll just say, you know, for. So I will encapsulate that into a function, right? But like for edges, for edge 2 in edges, right? To remove. It's not what the way that I want to do it, but yeah, okay. No, so I'll just do it like this, and I'll just say if mergeable edges, edge 1, edge 2, then new edge equals, well, merge them, right? And so, and what I would do now here is system hypergraphs, remove edge. Can I just search remove edge? Remove the single edge from a hypergraph. What happens to the nodes? We don't know. But I guess what I should do is I should add first a new edge, add edge, new edge, and then system remove edge, edge 1, system remove edge, edge 2, right? I'm sorry, I'm not so sure what will happen here because we're sort of iterating for each edge. We're going through everything again, so I don't know if you can really remove. I don't know if this is going to work out always, because if we remove things on the go, you know, it might just complain. What does it do if the edge does not exist? Remove edges for edge and edge set. Oh, it's actually, it can be. Oh, you can have set, remove edges. Remove edge. If edge in edges. Do it if not. Okay, so it doesn't spit an error. That's good. Um, so what about we now... It's like, well, we don't have to... So these I think I can all comment out for now. And so what we have, so we get the entanglement edges, and then we iterate over each pair of edges, and then say if they are mergeable, merge them, remove the two you've merged, and add the new one there, right? I don't know, see what happens. Boom. Node 272. This is probably, again, I think, the remove edges. It can happen. I think it could be that it's not working as expected in terms of... Okay, so what if we don't remove any edges? Because I think the problem is we might be leaving some nodes orphan or something. Oh yeah, nice. Okay, that's impossible to read. That's definitely impossible to read, but what I can do, just like, I just want to know, print new edge elements. Oh, quite a lot of new edges, that's not good. That is definitely not good. Well, the thing is, yeah, the thing is, of course, it's doing these. It's just because we're iterating over every single pair of edges, and we shouldn't be doing that. So we should be doing for each edge one, go over all the edges, and to be honest, that's it. Like, you pick one edge and go through all of them. No, that's not it. We should not visit edges that we've already visited in this loop. Right, so once we're done with edge one, then how do we do this? What is the smart way of doing that? Smart way to iterate over these. Can I just numpy possible pairs elements in the vector? I'm so lazy. Ah, look at this. Using numpy to build an array of all combinations of two arrays. No, that's not what I meant. Tools combinations module. Oh, so there's something there. So I have this array. Oh, look at these. Oh, that's nice. So there is something. So what is these? Give an array of size n, generate and print all possible combinations of R elements in array. Tools combinations. So docs Python for efficient looping. That's quite cool. Tools. So combinations. So do I have to import that though? How do I import that? Tools. Example. That's nice. That is definitely nice. It's super powerful, to be honest. What is the CPU on these? Am I really, is this really burning like 16%? That sucks. So I should probably import that. Or just NP IterTools combinations. Maybe that's what I want to do. Like, let's just keep this commented for a second and say NP IterTools combinations edges 2. Is this the way it works? Letters 3. Okay, and then this in iterable, right? So for print least combinations. Okay, so if I just say C is equal a least of all these combinations, and now I just say print C, what do I get? IterTools. Okay, that's not the way you import that. I get it from IterTools import combinations. From either, but is it then something? So I gotta import these. From IterTools import combinations. Okay, and now yeah. Yeah, this is going really slow. IterTools is not defined. Oh, it's just combinations. I'm just stupid. Just stupid. Okay, so these are all the possible combinations of... Okay, I like it. So, and now what I do is, I guess, so there's an entity here, another entity here. So what if I print C0? Is this 2 entities? Is this entity and entity? So that's 2 entities. So, okay, cool. So if I do, let me check. So, no, that's not what we need either. What we need is we need to iterate over all the edges, and once we, it's sort of like a greedy approach. Once we merge, then we move on to the other one. So what we do is for edge in edges, right? For edge in edges, what I do is for edge 2 in edges, right? So if edge different than edge 2, and they're mergeable, then we kind of, you know, we do the merging, right? So then we merge. So then we merge, and what we should do is we should now, instead of, we have found the edges that merge, so we should remove those from the list, or we should at least flag them. I don't like these, but like flagged. So this will be like an empty list. And so what I would do is, so I would just say flag append edge UID. Right? Is it UID or what's the? Is it UID or is it like map graphs, entities, UID? UID. So what I'm doing is so I'm adding these two, right? Edge 2. And so what I do here is mergeable and Python or NumPy in array. Is there some kind of in? Contains. Oh, there is zero. You can use 0 in A. Okay. So NumPy array and edge UID not in flagged and edge 2 UID not in flagged. I think that's what we probably want to do. So the edges are different, they're mergeable, and they're not like in flagged. And so here we add them in flagged. Pen NumPy, append. Can I just use a pen like that? Yeah, looks like. Okay. So flagged is not defined. So flagged and flagged, yeah. Now is it append? Oh yeah, because it's append, because it's probably np append something like this, right? Array and values, okay. The array and the values. So this is edge 2. Okay, so we have now less. It's still a lot, in my opinion, but it's less. What if I remove now? Is this gonna break? Yeah, it's gonna break. New edge elements. Or maybe it's just new edge. how many edges are we getting? So how many edges we're merging? That will be the question, right? Too many, definitely too many. We've got so how many we've got here? Print edges, length of edges, 4 edges, right? So we've got like, oh, why 4? Yeah, we've got 4 edges actually. Yeah. It could be that we actually have some 1, 2, 3, 4, 5, 6, 7, 8, 9. No, because we should just go like, hey, can we merge that? Yeah, it's merged. And then it's like, those are 2 flags, so we should really just flag 2 elements, right? Like, I know we should do 2 passes of these at the end of the day, but like we should just merge 2 edges. Oh, maybe UID and UID. That's what I should check, maybe. 4 and still a lot. 3, 6, it's the same 9, still 9. So if they're different, they're mergeable. And now question is, are we, so at the end, okay, let's print flagged. Okay, it's not working or what? Oh, of course. And I think I should just I can just combine that into, oh, there you go, 2 merges. Love it. That was the reason. Cool. Elements. Yeah. And now the question is, so now we have, one is like D state, right? And then D state, and the other one is D state, D state. Something's wrong. So what do we have? So we would have 0 and 0 plus 1, and then 1 and 0 plus 1. That's what I would assume we would have. And we have 0 plus 1, 1, and 1, 1. Okay. 0 plus 1, 1. That is weird. So, I'm just printing the elements of the new edge, so to say, right? Oh, because it's doing a different, so it's doing a different thing. It's doing, so the way this is working is it would do these and merge. And then it would do, I guess, these and these, but it shouldn't merge it anymore, right? Because now we flag them. So let's check which are the ones we're flagging. Print, I mean, we can check that, right? So we've printed print flagged. So we've in the first iteration we are flagging node 799, H799 and 802, which I have no idea. No, so I should actually edge elements and edge 2 elements, right? New edge elements. I'm not okay. New edge elements will be these in print. So I'm merging the 0, 0 with the 0, 1, and that gives us a this is wrong though, I think, right? It should give me, it's a 0 and it's a 0 for both qubit zeros. So why does it give me the state for qubit 0? Let me see, I'm doing something wrong. Oh, there you go, that's the problem. Okay, I was merging something else. Oh, bam, there you go. So we have the 0 and the 0. Sorry, the 0. So we have the 0 and the plus. Yeah, that makes sense. Okay. And so if I now print, and then here's the 1 and the plus. So it takes the 2 1s plus and 2 zeros and plus. That's nice. Okay, cool. And now we should do kind of okay. But if I remove things, then so if I remove, that's not gonna work for some reason, I think. Oh, whoa, whoa, whoa! This is also wrong. Oh God. So edge, edge, and edge 2. Yeah, that's a problem. I should let's stick to the edge 1 thing. Not flagged. Edge 1, edge 1, edge 1, edge 1. So if I run these, it breaks, right? It still breaks because it just node 866 is like, what the heck is this? It's been removed, and what does the remove edge? It probably doesn't remove the nodes from nodes. Right, yeah, okay, it does remove nodes. And if memberships, yeah, but we know that's not working well. That's gonna make my job complicated here if I cannot trust on the remove edges, because the memberships don't seem to be updated in the memberships at the nodes level. So if I remove these, it's just 1. It won't work well. At that point, I'm thinking to just create a new system from scratch out of these. But that's not. Maybe I can do that for test purposes now, but like as long as this is not fixed, I'm gonna have a hard time figuring like how to remove the edges properly. But I'm adding the new edge. Maybe I can try that system tool. So how does entity system blah blah blah. Okay, it's hypergraph, just like that, HNF hypergraph. So why don't just like, just for the sake of testing, right? System tool hypergraph. In theory, the if I add this to system tool, that should add the nodes as well. And if I print system tool at the end, let's see. Yeah, okay, that adds this to now this. But why are those nodes not having the state set up? I have to figure out a way to. These sites, it doesn't seem to be working well. The whole removal thing. But I think I'm getting that correctly. The thing is, I need to do, I guess, still two. Like in this case, I would need to do two passes, right? Like I have, because I've added two new edges, and I would still need to do another pass for these. So the function would look like. So for the function, I would have to kind of. Yeah, I think I'm gonna leave it here now because it's already a bit late. But I'm promising more videos soon. I'm gonna be doing more videos next week. Cool. But I think that I'm on the right path here. I'm definitely on the right path. So that's definitely stuff that we can remove. And it's just does not. Sorry, system. It's just messy. Because okay, so these are the two nodes. There you go. So it's also printing them, even though I haven't added them to the system. Oh no, yeah, I have added them to the system. Okay, cool. But I haven't added them to the qubits. That's why, to the qubit edges. Oh. I merge them. Merge edges, but because I'm creating the node. Yeah, but I'm adding it to the qubit edge. Come on. It's like you gotta be kidding me. I'm adding it to the qubit edge. Yeah, whatever. But now because these two would be equal for 8 and 4, 5, and this is 0 and 1, then we would get like, if we would do another pass, we'll get like what we want, which is exactly like a plus and a plus. So that works well. I just need to now encapsulate that into a function and figure out how to add these things correctly. But I think that's it. That's definitely it. And I mean, wait a second. No. That's definitely not it. What happens with the amplitude? So these we've got a big to-do here, which is okay. They can merge, but now the merging, right? So this is all good. We're merging, but there's a big to-do here. What happens with the amplitude of the edge? I mean, that's wrong naming, right? But it's the number, right? That we were having, like here, right? These number here, the edges having this amplitude in here. Yeah. that's what's not clear yet in terms of what do I do with these as I merge. But it's merging correctly, at least. It's merging things correctly. It just has 0 amplitudes for the moment. So this is a to-do. Okay, cool, we're getting there. We're getting there.